10.4, we're going to look at dividing radical expressions. In this section, we only have one rule or one property of radicals. This is the second property of radicals for us. The previous section, section 10.3, we looked at the multiplication rule of radicals. So, here what the quotient rule reads, pretty straightforward. The word quotient here means fractions or division, right? So anytime we have a fraction under the radical sign, in this case a over b, it is possible to split the radical into two separate radicals, a numerator and the denominator. And of course the index n will be the same for both of them. True? And there we have that one. So again, the quotient rule allows us to break up all the radicals that have fraction inside the radicand as the division or quotient of two separate radicals, one on top, one on the bottom. So let's take a look at number 12. In number 12, we're going to find the square root of 81/25. Now the question is actually asking very specifically to simplify by taking the roots of the numerator and the denominator. So if you were to do this, let's say in the first section of chapter 10, when we define the square roots, we're going to say, okay, well, I'm looking for two fractions whose product's going to be 81/25. So that's going to be like 9/5 times 9/5, right? So the answer is 9/5. That's how we did it in section 10.1. Now in this section, to use the property, we're going to actually break it into square root of 81 on top square root of 25. So we're thinking about two separate numbers here, whereas we looked at a single number, 9/5 as a fraction, a single number on the number line. Now taking the root of 81, you get 9. Taking the root of 25 is 5. See, we think of this now as two separate numbers rather than one fraction, one whole fraction. Okay? And that's doing it the way they wanted in this section. So to do something like number 16, here we have a numerator over a denominator, and that's going to be 12, and square root of p squared is p. Remember, we assume the variables are positive. That means no need for absolute value. If we didn't make that assumption, we would have to put absolute value on p, because that guarantees the answer will be positive, the principal root, the positive root. Let's take a look at something like number 20, for example. In number 20, I have the cube root, actually 64x7 and 216y6, and we got the cube root of that. Okay, so let's break it into a numerator and into a denominator. Now note, each of the numerator and denominator are in the form of a product individually. So we're going to use the product rule that we learned about in section 10.3. So that means I need to do cube root of 64. And let's see, cube root of 64. I'm going to do this a little differently. Now 64 is what? 64 is 4 cubed, isn't it? So that's a perfect cube. In other words, cube root of 64 is just 4. Now for x to the 7th, you can think of it as x cubed times x. Or in the previous section, remember we did a long division of 7 divided by 3, quotient 2, subtract 1. Remember, this is going to be inside, this is going to be outside. So that still works. In the denominator, 216. Now 216, let's see, that one is going to be what? 216, that, let's see, 216 divided by 64. Let's see, 216, let's see, two numbers, one of them perfect cube times another gives me 216. Actually, 216 is perfect cube, and that's because 6 cubed is 216. 6 cubed. Okay, now y to the 6th, I'm going to go y cubed. And then we can do this one now. So that's going to equal to cube root of 64 is 4 on the outside. Now, the first x come out, second x comes out, the cube root of x remains. Divided by cube root of 216 is 6. The y comes out, another y comes out, nothing remains under the radical. So the answer to this is 4x squared times cube root of x all over 6y squared. And we're done with this one. Okay, number 20. Let's take a look at number 30. In number 30, now you're given a split fraction, a numerator and a denominator. The question asks us to divide and simplify, assuming variables are positive. Now for this one, because it's already split, let's actually put them back together. That's the reverse of the quotient property. Let's put them back together. That's 700x divided by 7x. Now 700 divided by 7, that's going to be what? 100. The x's cross out. That's the square root of 100, or it's just 10. And there we have this one. If we look at number 32, so the answer to that is just 10, the one we just did. Cube root of 35 divided by cube root of 5. Now 35 by 5 is 7, isn't it? There, if we write it as 1. And the answer is cube root of 7. Okay. Let's take a look at number 38. In number 38, I have square root of 75ab over 3 root 3. So I'm going to keep this 3 away from the action, okay, and combine 75ab with the other 3, okay, the one that's under the radical. Now 75 divided by 3, that's going to be 25, right? So this is just 25ab. And square root of 25 is 5, so that's 5/3 times root ab. Okay, and there we're done with number 38. Let's take a look at number 44. In number 44, now the question here is rationalize the denominator. Rationalize the denominator. Okay, now assume all variables are positive. The number is square root of 7/2. Now, here's what it means to rationalize the denominator. So we have a fraction under the radical in the radicand, right? Let's break this into square root of 7 and square root of 2. Now, if you note square root of 2, this is irrational. Any square root or any index for the radical, if the radicand is not perfect power of the index, in this case 2, if the number is not perfect square, the answer is going to be irrational. Now, here's something we can do to correct this, to do what they want us to do, to rationalize. So right now, the denominator is irrational. If I multiply top bottom by the same number, I haven't changed that problem, because it's like a 1. Let's multiply by 1. Now in the numerator, I have 7 times 2, that's going to be 14. In the denominator, root 4, and square root of 4, of course, is 2. Now 2 is rational. So this process of taking an irrational denominator, turning it into a rational, it's called rationalizing the denominator. That's what we just did. Okay. So that's it. We're done with that one. So when we say rationalize the denominator, means we do not want radical signs in the denominator. Now let's take a look at number 48. In number 48, we have a cube root of 2/9. So let's break it. Cube root of 2, cube root of 9. Now, be careful here. Cube root of 9 is not 3. Square root of 9 is 3, but not cube root. So, now remember, because we have cube root, we need perfect cubes. Now 9 is 3 squared, true? If we multiply 9 times 3, that becomes 3 cubed, right? That's like multiply both sides by 3, and that's what happens. 3 cubed, that's perfect cube, isn't it? So that means I need to multiply top and the bottom by cube root of 3 in order to produce perfect cube in the denominator. And check this out. See that? Cube root of 27 is 3, because 27 is perfect cube. Now in the numerator, I'm just going to multiply 2 times 3, right? 2 and 3 multiply together. And then I'm going to multiply 2 by 3, and that's cube root of 6, and we're done with this one. Notice again, rationalize denominator means no radical in the denominator. And as you can see, there is no radical in there. Okay. Let's take a look at number 50. In number 50, we have cube root of 7x divided by cube root of 3y. Now for this one again, I want to multiply by perfect cubes, right? Remember, for perfect cube, that means I need to have 3 of that factor to create perfect cubes. I have a single 3 here. I need 2 more 3s, don't I? Means multiply by 9. That will give me 27, and that's perfect cube. On the variable side, we only have a single y, because the index is 3, right? The index is 3. That means I need 2 more y's. Now, when I multiply them, you can see what happens here in the denominator. 3 multiplies by 9, right? 3 times 9, that's 27. That's 3 times 9. That multiplies to 27. That's perfect cube. And then y squared is y cubed. The numerator is cube root of 63xy squared. Okay. And there we have this one. The denominator is going to be 3y. And that's what our goal was. And in the numerator, whatever happens, doesn't matter. Notice the numerator gets more complicated. But that is okay. We accomplished what we wanted to. That's number 50 for you. Let's do number 56. Number 56, I have square root of 3x divided by 20. And we want to rationalize that denominator. That's 3x over root 20. Now, here's something I'm not going to do. And this is what I'm not going to do. So I'm going to erase this, okay? There. I'm not going to do that. Why? Although that gives me 20, but in the numerator, I'm going to simplify when I multiply 3 times 20, 60. So there's no way out of this simplification. So might as well simplify square root of 20 from the get-go. So what does that mean? That means, well, let me do that over on the side. Well, square root of 20, isn't that the square root of 4 times 5? And 4 is perfect square. Its square root is 2. So the denominator is just 2 root 5. And I'm going to now notice 2 is out, square root of 5. So we want to rationalize the square root of 5. Let's multiply top bottom by root 5. There. And that's going to do it for us. Next step, we'll be done with this. 2 and root 5 is, if you want to write it, is root 25, which gives you the 5 back. When you multiply two square roots with the same radicand, you get the radicand back. Okay, now in the numerator, we have square root of 3x times 5, true? It's root 3x times root 5. That's from there. Now we can multiply 3x times 5. The answer is going to be what? 15x. And 2 times 5 is 10, so might as well finish it off that way. Divided by 10. And that's the final answer in this one. Okay. Now we just learned how to rationalize the denominator. We can just as easily rationalize the numerator. Rationalize the numerator this time. That means the top. So number 62, we have 2/3. First, I need to break it off into two radicals. And again, the focus is on the numerator, right? Let's multiply by root 2, bottom by root 2. That makes it root 4, root 6, and square root of 4 is 2. So there's the answer to this one. 2 divided by root 6, or root 6. Let's take a look at, for example, number, how about number 64? Let's take a look at 64. I guess with these, the more you do, the better you feel about it, right? The more the merrier. Okay, we want to rationalize the numerator. So the only thing in the numerator that's in the radical is a 10. So here's what we do not want to do. We don't want to multiply top bottom by 3 or top bottom by 2, nothing like that, because those are not radicals. Okay, so the only radical in the numerator is 10. So we're going to do top bottom by root 10. Okay, now root 10 is root 100, and that's just 10. Okay, so this gives me 30. That's the top. Now the bottom is root 3 times root 10, so that's 2 root 30, right? 10 by 3. And that's going to stay throughout. Nothing changes there. And with that, we're done with number 64. Again, if you note, oh, actually I can simplify now, couldn't I? Yeah, I could have done it up here, or I can do it here still. I get another chance. So let's write the final answer. 15 over root 30. We always simplify fractions to the lowest form, lowest terms, or reduced form, however you call it. Now for something like, for example, number 69, just to do one last one here, I have root 7x over 3y. Okay, now first we're going to break it off. And then we're going to multiply by, what are we going to multiply by? We're going to multiply the top by root 7x and the bottom by root 7x. And that gives me 7x, right? Root 7x gives 7x. In the bottom, I get square root of 21xy. And we are done with this one. Okay, so in section 10.4, we're done with that section. Our objective was to get rid of the, not get rid of, that was just part of it. But the objective was actually this, to learn about the quotient rule, which allows us to simplify fractions under the radical symbol. And with that, we are done with section 10.4.